Hello everyone. We are going to continue our discussion of the kinematics chapter. Specifically, we are going to continue our discussion on the section of quantification of deformation. So in the previous part of our lecture, we had arrived at this equation, and we had mentioned that we are going to mathematically manipulate this particular expression, that is the difference between the displacement vectors of the point Q and the point P. So in order to motivate that discussion, let us first quickly write down the explicit component-wise forms of this equation. So what I basically mean is dx1 will be d capital X1 plus u1 x1 plus d x1 x2 plus d x2 x3 plus d x3 minus u1 x1 comma x2 comma x3. So this is just the first component of the d small x vector. Similarly, we have for d small x2 d capital X2 plus u2, again a function of x1 plus d x1 x2 plus d x2 and x3 plus d x3 minus u2 x1 x2 x3. And finally, for the dx3, similarly we have d capital X3 plus u3 being again a function of capital X1 dx plus dx1 x2 plus dx2 x3 plus dx3 minus u3 x1 x2 x3. So this was quite repetitive and I'm sure quite boring, but anyway, the benefit of having written it out explicitly like this is basically to motivate that if you just look at one component, let's say dx1 or equivalently dx2, you see this is basically this part, this entire part, the difference between the two position vectors, or the first component of the position vectors u1 here and u1 here. This is basically a function of three variables. This also is a function of three variables, but the functional dependence is in such a form that here it is x1 and here it is x1 plus dx1. So by a small increment, a difference by a small increment, here it is x2, here it is x2 by x2 plus dx2, and here it is x3, and this is exactly x3 plus dx3. So in each of these three component wise dependencies, there is only a small increment. So perhaps this gives us an idea that it will be beneficial to expand this using Taylor series expansions. But the only problem is that from our previous lessons of Taylor series expansions, what we are mostly familiar with, I'm sure, is the Taylor series expansions of functions which have only one kind of functional dependence. So what we are going to do very quickly here is a brief refresher of Taylor series expansions. So first of all, if we have something like f of x plus dx, and please note that from in this little refresher on Taylor series expansion, whenever I'm going to write this small x, it has no connection whatsoever with these previous dependencies. This is just a general mathematical dependence. So this is just like your first year mathematics. So f of x plus dx, that is given by f of x plus dx by factorial 1, first derivative of f of x with respect to x plus dx square divided by factorial 2 f double dash x plus higher order terms. This you are all familiar with. But suppose now we have, instead of the dependence on only x plus dx, suppose we have some kind of a dependence on another variable y. So suppose we have a thing like this: x plus dx, y plus dy. Then what? Well, for the first term, as you can imagine, this will be just the f dependent on x and y, and then we'll again have the first order term like this. But now, instead of the f dash x, we have to remember that because f is a function of both x and y, the derivative of f with respect to x has to be taken in the form of a partial derivative. So this is del f del x, but the dependence on y also has to be accounted for, and that is done by writing it exactly like the dx part. So this is dy by factorial y del f del y. So this is the first order term. For the next order, we again have dx square by factorial 2, and this time we have del square f del x square, and we have the y square by factorial 2. However, this is not the end of the story, because we'll also have some kind of a cross dependence involving both the dx and dy, because this is now a quadratic dependence. So it will be twice dx dy by factorial 2 del square f del x del y, plus we are going to have some higher order terms. Alright, now you can see that slowly we are building up to dependence on 3 variables, and that will be useful to us when we go back towards the simplification of these displacement vector components. So we can write down the 3 dependencies going forward to x plus dx, y plus dy, and z plus dz in the next slide. So this is the thing that we have extra here: dz by factorial 1 del f del z. Now if I want, I can possibly go to the second order terms, but I don't want to do that, because remember that my purpose here of doing all this brief reflection on the Taylor series expansion, is to actually mathematically manipulate this, and for that purpose I do not need to consider these higher order terms. So all that I want is to go up to the linear or the first order terms. So I'll stop the the writing out of the terms up to here, and by comparing this f of x plus dx, y plus dy, z plus dz with the u1, for example, as it depends on x1 plus dx1, x2 plus dx2, x3 plus dx3, I can write down the Taylor series expansion of this term. Okay, so going back to the dx1 component, so I take a look at this again. So this thing will be expanded in exactly this fashion. So what do we write here? u1, x1, x2, x3 plus the x1, and I do not anymore write divided by factorial 1 because that is just 1, and del u1 del x1. You please note the similarity of this term with this term. Okay, so going forward, dx2 del u1 again del x2. Again, you note the similarity of this with this, and please be very careful to note that this is still u1 here because we are actually dealing with the expansion of this u1 here, this entire thing. This is completely separate. The u2 and the u3 are completely separate. Okay, and finally we have dx3 del u1 del x3 plus dot dot dot, and please do not forget that we have this term remaining at the end, the u1 x1 comma x2 comma x3. So we have to write that down also. You see very quickly that this term, it cancels with this term, so that's very nice, and we end up with a very nice convenient form which can be written in a very nice clear way in operator form like this. That entire thing goes in a bracket, and that entire thing, like an operator, it operates on the variable u1, and of course we have the higher order terms here which I'm not going to write anymore. So what you can say is that the dx1, because I'm no longer writing the higher order terms, this is no longer an equal to, so this is now the Taylor series expansion, or the Taylor series approximation for the d small x1. In a similar fashion, if I go back and look at my dx2, you will note that I have to expand in terms of this u2, and I can directly write that down as dx2 is approximately equal to d capital X2 plus this entire operator will remain as it is, but this time this is going to operate on u2, and similarly for dx3 I will again have this to be approximately equal to dx3 plus this entire operator again, dx1 del x1 plus dx2 del del x2 plus dx3 del x3, operating this time on u3. Now you note that this entire operator, it is convenient and it can be written in a further in a still more compact form by noting that this is almost like so let me write this down quickly. So this operator, dx1 so this thing is like the dot product between the dx vector and the gradient operator. Well, that seems like a massive leap, but actually it's very simple. So we can quickly note it down in the rough column here that the dx vector that has the components dx1, dx2 and dx3. So these are the three components of the dx vector, and the gradient operator, that is nothing but having the different components as del x1, del x2, del x3. So I hope you can remember this from your first year vector calculus. So if we substitute this particular expression back here, then this becomes even more simple. So d small x1 is equal to d capital X1 plus dx vector dot grad u1. Similarly, dx2 is equal to d capital X2 plus dx vector dotted with the grad operator operating on u2, and finally dx3 is equal to d capital x3 plus d x vector dotted with the grad operator on this. Now all these three things together, they can be further shortened into the vectorial representation as this, because you note that dx1, dx2 and dx3, they are themselves components of this d small x vector. Similarly, the d capital X1, d capital X2 and d capital X3, they are the components of the d capital X vector, which you have already written here, plus this is already in vector form, grad. This entire operator is operating on the vector u, because you note that u1, u2 and u3 are nothing but the scalar components of this u vector. So this is a very useful, very compact notation that helps us to go forward with the quantification of deformation. Okay, so in the next part of our lecture, we are going to see how this expression, which incorporates within it three different expressions, these can be utilized in the context of our discussions of string, which will be a major topic within our chapter of kinematics.